Hello again. In this video, we're going to go over the mean value theorem for integrals. So here's what the mean value theorem for integrals says. Let f be continuous on a closed interval from a to b. And there exists a point c in the closed interval from a to b such that f evaluated at c is equal to the average value of f on the closed interval from a to b. And if you remember, the average value of f is equal to this little formula, 1 over b minus a times the definite integral of f of x from a to b. Okay, so a couple of things here. Notice that there's really just one condition that you have to satisfy for this theorem. You just need to make sure that your function is continuous on a closed interval. In addition to that, notice that this is what we call an existence theorem. It guarantees us the existence of this point c in this closed interval from a to b such that f evaluated at c is equal to the average value of f on the closed interval from a to b. Okay, so it's an existence theorem. Now, let's suppose we satisfy the conditions of this theorem, right? So we have some function that's continuous on a closed interval from a to b. Okay, and let's find the average value of this function using this little formula. The average value of that function on the closed interval from a to b would be right here. So that's f bar. Now notice that since the function is continuous on this closed interval from a to b, that f bar must intersect the function at some particular point, which we're going to call c. And notice that c is contained in this closed interval from a to b. So in other words, if f is continuous, it has to get from this point to this point in a continuous fashion. Then it would have to cross its average value, which is somewhere in the middle, right here, at some particular point. And that particular point needs to be somewhere in this closed interval from a to b. That's all this theorem says. I think you can see why you need continuity on the closed interval from a to b. If f of x is not continuous on this closed interval from a to b, then you could jump over this average value, right? Your function could be right here, and then you could just discontinuously have it jump over that line and then continue on. So you do need to have continuity on this closed interval from a to b. Okay? Okay, so let me do an example where we use this theorem. Okay, so let's suppose our function is x squared. By the way, the graph of x squared looks like this. And let's find the average value of this function on the closed interval from 0 to 3. Okay, and here's our formula for the average value of a function. So it's going to be, a is going to be 0, and b is going to be 3, because we're trying to find the average value of this function on this closed interval. Okay, so it's going to be 1 over b minus a times the definite integral from 0 to 3 of x squared. Okay, notice x squared is continuous on the closed interval from 0 to 3. And so we can use the fundamental theorem of calculus to evaluate this definite integral. So we just need to find any antiderivative of x squared, which is x cubed over 3 plus any constant. And we're going to let that be 0. Remember, we just need any antiderivative, so pick the easiest one. And that would be the one where the constant is 0. And then we just have to evaluate this at the upper limit minus the lower limit to get that definite integral. So it's going to be f of 3 minus f of 0 times 1/3. Okay, so f of 3 is 3 cubed over 3. And of course, f of 0 would just be 0. And so notice here you're going to get 27 over 9 after you distribute that 1/3. And 27 over 9 is equal to 3. Okay, so the average value of this function on this interval from 0 to 3 ends up being 3. So it's right here. Okay, so then let's find the point C. So remember that the mean value theorem says there exists some point C in the interval from A to B, closed interval from A to B, such that f of C is the same as the average value of the function on that closed interval from A to B. So let's find that C value. Okay, well, the way we can do that is we know the average value for this function is 3 on the closed interval from 0 to 3. And now we can find f of C is C squared. Okay, just plug a C in for the function. And now we can find the C. Right, so C would have to be, now take the square root of both sides here, right, to solve for C, and you get plus or minus the square root of 3. Remember, there's two answers to this. The square root of 3 squared is 3, but also negative square root of 3 squared is 3. So there's actually two answers here. Okay, so it's plus or minus the square root of 3. Okay, so notice that in the diagram here, square root of 3 has to be between square root of 2 and square root of 4, right? Square root of 4 is equal to 2. And actually, let's say square root of 1. And square root of 1 is equal to 1, right? Square root of 3 is between square root of 1 and square root of 4. Square root of 1 is 1, right? And then square root of 4 is 2. So square root of 3 is somewhere between 1 and 2. Okay, so it's in here somewhere. And I haven't drawn this accurately enough. So square root of 3 is where this intersects the function. Right, so if you draw a line, a horizontal line at 3, at y is equal to 3, it's going to intersect this function right at square root of 3. That's our C value. But it also intersects on this side, right, at negative square root of 3. Okay, but square root of 3 is the only one that's in this interval. That's, remember the theorem says there exists at least one point in this closed interval from A to B. There could be more than one, right? In our case, there's only one. Okay, now there's another one over here, but it's not in this closed interval. Okay, so this is the point that's guaranteed to exist. Okay, and you can just check it to make sure. When you say f of C, you get square root of 3 squared, which is 3, and that's equal to the average value of this function on this closed interval. Okay, so that's an example of an application of the mean value theorem for integrals. Okay, so I hope you found this video helpful. Thank you for watching. Bye-bye.